Hi mathematicians, welcome to my first video on my channel. In this video I'll be deriving a formula for the sum of nth square natural number. In summation notation we can write it as sum from k equals 1 to n of k square. The prerequisite for the proof is shown in my presentation. So you should know the sum of the first n natural number, which I'll be deriving in my next slide. Also, you should know the formula for a plus b quantity cubed, which is left to the viewers to prove it. The proof of the sum of first and natural number is as follows. For all natural number n, we define s to be equal to sum from k equals 1 to n of n, which we can also write it as s equals 1 plus 2 plus 3 plus all the way up to n. So if we arrange the above equality from last to first term, we obtain s equals n plus n minus 1 plus n minus 2 plus all the way up to 3 plus 2 plus 1, which I'll mark it as equation number 2. So if we add the first equation and second equation, we get 2s equals n plus 1 plus n minus 1 plus 2 plus all the way up to 2 plus n minus 1 plus 1 plus n, which is equal to n plus 1 plus n plus 1 plus n plus 1 all the way up to n plus 1, which has n terms in it. So we can write it as n times n plus 1 because it contains n terms. Hence, dividing both sides by 2, we get s equals n times n plus 1 divided by 2, which is very useful in our proof. So our main proof starts here. We use difference equation approach. Define for all natural number n, t equals sum from k equals to 1 to n of k squared. So which we can write it as t equals 1 squared plus 2 squared plus 3 squared plus all the way up to n squared. So note that by using the formula which was left to you guys to prove, we can write it as m plus 1 quantity cubed equal minus m cubed equals to m cubed plus 3m squared plus 3m plus 1 minus m cubed, which is equal to 3m squared plus 3m plus 1. We substitute some values to the equation that we just derived. So for n equals to 1, we get 2 cubed minus 1 cubed equals to 3 times 1 squared plus 3 times 1 plus 1. Similarly, for m equals to 2, we get 3 cubed minus 2 cubed plus 3 times 2 squared plus 3 times 2 plus 1. So we calculate it all the way up to m equals n minus 1, which is nothing but n cubed minus n minus 1 cubed, which is equal to 3 times n minus 1 squared plus 3 times n minus 1 plus 1. And for m equals to n, we have n plus 1 quantity cubed minus n cubed equals 3n squared plus 3n plus 1. So we add all the equalities that we derived before. First of all, we notice that most of the terms in the left hand side cancels out. So we get n plus 1 quantity cubed minus 1 cubed in the left hand side. So in the right hand side, we notice that 3 as a common factor, and we get 3 times 1 squared plus 2 squared plus all the way up to n minus 1 squared plus n squared, which was our desired sum, plus 3 times 1 plus 2 plus 3 plus all the way up to n, which was our first and natural number formula which we had derived before. And we get 1 plus 1 plus 1 all the way up to 1, which contains n terms. So we get n plus 1 cubed minus 1 cubed equals 3t plus 3s plus n. But we know that s equals n times n plus 1 divided by 2. So we have n cubed plus 3n squared plus 3n plus 1 minus 1 equals 3t plus 3n times n plus 1 divided by 2 plus n, which we can take the common denominator and we can multiply both sides by 2 to get 2n cubed plus 6n squared plus 6n equals 6t plus 3n squared plus 3n plus 2n. So at last we solve for 6t and we have 6t equals 2n cubed plus 3n squared plus n, which we can factor out the n and we get 6t plus 2n squared plus 3n plus 1, which we can further factorize it as 6t equals n times n plus 1 times 2n plus 1. Therefore we have t equals to n times n plus 1 plus 2n plus 1 divided by 6, which is our required sum. So at last we have sum from k equals 1 to n of k squared equals n times n plus 1 times 2n plus 1 divided by 6 as desired.